Good morning. This is the first in 3 lessons that are going to focus on applications of quadratics. In other words, what do we use quadratics to model in the real world? We spent about 9 days just figuring out how to factor, and then several days on how to solve quadratic equations, but what we haven't touched on is why would we ever want this or need this in the real world? How does this connect to the world that we experience every day? So the goal for this lesson is just to simply visualize parabolas that we see all around us every day. And one of the most common applications for parabolas is something called projectile motion. This would be anything that is thrown or tossed or dropped, even like in free fall motion. And if you have studied physics, then hopefully you've encountered this before. What I want to start out with is just to quickly summarize what we know about parabolas from the last 2 units. So we talked in the last unit about some key points on a parabola, and this figure might look familiar to you, where we have the XY plane and then we have this parabola on it. And there are several key things or key points that we can find on this parabola. For example, we have right here that I'm highlighting in blue, we have the y-intercept. Remember, the definition of the y-intercept is the point where the graph crosses the y-axis. There is only one. Then we have the x-intercepts, and a parabola would have 1, 2, or none of these. Okay, these are called the x-intercepts, and there are 2 other words for that. They are the roots and what are called the zeros. And they're called roots. I can kind of like picture them as being like the root, if this is like a tree or something, the roots are going down beneath. Or they're called zeros because the y coordinate is equal to 0 at that point. And the other key point that we looked at was the vertex, and that is where the parabola changes direction. It's also like the highest point on the parabola or the lowest point on the parabola, depending on which way the parabola is flipped. And we'd also call it the maximum or the minimum. If you have a graphing calculator, then we can use the graphing calculator to find maxima and minima. Now, we've also explored how to find each of these points. So we have in place at this point the mathematical knowledge that if I were to give you an equation for a parabola, you would be able to find the vertex. You'd find the x-coordinate of the vertex and the y-coordinate of the vertex. You could find the y-intercept, and you also now have the skills to be able to find the roots, even though we haven't quite talked about that in the context of the equation yet, but we will. All right, so to find the y-intercept, okay, here's what we want to remember. We set x equal to 0 and solve for y. Now, why we do that is because on the y-axis, the x-coordinate of any point on the y-axis is equal to 0. So if you want to know the y-coordinate that goes with that, namely where the graph crosses the y-axis, you would plug in x is equal to 0. Now, a similar process works for the x-intercepts. You would set y equal to 0 and solve for x. And that's what we've spent the last several class periods doing. Back when we talk about like solving quadratics by factoring or using the quadratic formula, remember that we want to use the zero product property. And so the first step for those is get a 0, set it equal to 0. We'll set it equal to 0 and set y equal to 0 are actually the same thing. So you would plug in a 0 for your y, and then you would go about solving the equation for x, which again is what we've been doing. We've been taking these equations and figuring out what the x is, and sometimes we have 1x and sometimes we have 2x's, and that's why we're getting these 2x values out. Now, the vertex is actually from the last unit. I just realized that there's a cat in here with me. Cool. Anyway, the vertex is actually from the last unit. So this is a little bit older and is part of the reason why I want to do this quick little review. For finding the vertex, to get the x coordinate, we use that formula, the opposite of b over 2a, and then to find y, we simply plug x into the equation. So we would use that formula there to find the x coordinate of the vertex. And then if we wanted the y coordinate of the vertex, we would take that number and plug it into the equation and we'd get the y. So hopefully that sounds familiar now that I say it. So like I said, the goal today is to actually look at some word problems and be able to picture the parabola. Because when you're doing a quadratic application problem, you can be asked a whole bunch of different things. Like you can be asked, well, let's actually take a look at an example. I'll give you one that we can look at. Okay, so we have here my amazing artistic skill here. We have a person, and the person is throwing a ball. Now, when I do this in class, I will often actually throw something in class, so the class can see the parabola. But for those of you that are doing this through video, you toss something across your room. I don't hit anybody or break your mom's favorite lamp or anything like that, but you all know, because you've all thrown things at some point, that when it leaves your hand, it arcs upward and it goes upward for a while and then it comes back down and it hits the ground. Now, what we have there is a parabola. And if you had an equation that would model the motion, then you could figure out different things about like how high did it go, or where did it land, or when did it land. There's actually two variations on it. One where you have like the height with the y distance, and then you have the x distance, and this could be like if you're throwing a football or a baseball and you're throwing it away from you. The other way you can do it is you have the height, and then this would be time, and so it would tell you when the ball hits the ground. And so if you have a t in the equation, probably what you're dealing with is time, but it's going to be beneficial for you to picture the parabola this way. Now, if we were to put the XY plane over it, then we should be able to recognize some of the key points that we were just talking about. For example, when the ball or where the ball leaves my hand, that would be the y-intercept. The vertex would be how high the ball got, or where the ball was when it got that high, or when. And that gets into your like x coordinate of the vertex and versus the y coordinate of the vertex. And then where or when the ball hits the ground is your x-intercept. So what we want to do today is we're going to look at 8 word problems. We are not going to try to solve them. We're not even going to spend a whole lot of time looking at what we're being asked to do. That we're going to save for tomorrow. Today's goal is just to be able to read a problem and picture the parabola involved in this problem. So without further ado, I am going to look, there are 9, I think actually, no, I'm only giving you 8 task cards that you're going to have to draw a picture to model it and then label the y-intercept, the vertex, and the x-intercepts. And possibly just identify what each question is asking you for. I'm going to do 2 examples, and then you're going to break up into your small groups to finish them out. If you don't finish them in class, then that is going to become your homework, and you can divide it up in your group however you want. I would strongly encourage you, even if your group mates are doing some of the questions, that you go back and look at their answers and make sure that you agree with them. So let's take a look at task card number 1. So this is task card. Whoa, that was my Boston accent there for a second. We have a task card here. Task card here, which is task number 1. So we're going to read the description, and then we'll look at what we're going to try to draw it out, and then we'll look at the different questions and try to figure out what the question is asking us for. Again, today we are not actually going to find any of those things. We are just going to try to make sense out of the problem. So your nephew is standing on his deck, that would be a porch, which is 4 feet off the ground. He tosses his toy up into the air at an initial velocity of 7 feet per second. The equation h equals negative 2t squared plus 7t plus 4 models the toy's height h in feet from the ground at t seconds after he threw it. Question A, how high is the toy after 1 second? Question B, what is the toy's maximum height? And C, how long is the toy in the air? So before you get overwhelmed by that, and it just seems like too much stuff, I want to point out a few things about it. In the problem, they are giving you different pieces of information. So you know that the deck is 4 feet off the ground. You know that the initial, that means starting velocity, is 7 feet per second. But you don't actually need to do anything with that information. If you look at the equation they give you, the 7 and the 4 are already in it. So don't let that overwhelm you and throw you off. What we're going to do is just draw a picture of your nephew throwing the toy off the deck. So this is what you are going to do in your assignment. So here's like the house, okay? I'm going to put the house here, okay? We have the house. And then off the house, we have a deck. That's our porch, okay? So this is the house. We'll put like a window in it, okay? And we'll put another window. So there's your house, or your nephew's house. And there's the deck. Here is your nephew standing on the deck. And the nephew is throwing the toy. Now, what we don't know is whether the toy is being thrown. If you watch the video here, we don't know whether the toy is being thrown out like this, so it's going to land in the backyard somewhere, or whether the toy is being tossed up and then coming back down. Here's the key. It doesn't actually matter. So what we're going to do is draw this so that we're seeing that arc going across the yard, just because it makes it easier for us. So I'm going to use green for the green grass in the yard, and I'll change the color. We'll use orange for the path of the toy. So the toy is going up, and then the toy is coming back down, and it's landing lower than it was to start off with. Again, doesn't matter. What I want you to do, now, you kind of draw your picture, okay? And we're picturing the parabola. There's the parabola. Now we're going to try to label the y-intercept, the x-intercepts, and the vertex. Start with whatever is easier for you. So for me, the easiest point for me to see is the vertex. So I'm going to go ahead and label it vertex. Now, in order to figure out your x-intercept and your y-intercept, you actually need to envision the xy axis on top of this. Always put your x-axis, I'm going to change color over to this gray color. Put your x-axis at wherever the object is landing. And then put your y-axis through wherever the object starts. So there's the x and there's the y. Once I do that, I can see that the y-intercept is where your nephew lets go of the toy, and the x-intercept is where the toy lands. Now, before somebody thinks, wait a minute though, there is another x-intercept. It's in back of your nephew who's throwing the ball. So when you do the math calculation, you're going to get 2 answers, but only one of those answers actually makes sense in the context of the problem. So just kind of be aware of that. So that's what I want you to do today. You're going to read the descriptions and then draw a picture of it and label the vertex, the x-intercepts, and the y-intercept. That's it. Now, if you want to, you can go back and do this. So let's take a look at the questions. The first question is, how high is the toy after 1 second? Well, we want to think, does that correspond to any of the points here? At 0 seconds, we could give the height there, but we don't actually know when the toy hits the highest spot. We know your nephew's going to let go of the toy and it's going to go up. What we don't know is exactly where in there the 1 second is. So we don't know if it's 1 second here or here or here, or maybe it actually hits the ground by the time 1 second has gone by. So we don't know that. So we're going to leave that part blank. Next question, what is the toy's maximum height? Well, the toy's maximum height, that's going to be right here. It's going to be at the vertex. So I'm going to come over here and just label this vertex. Okay, because I know for part B, I'm going to be finding the vertex. Whether you want the x coordinate of the vertex or the y coordinate of the vertex, that we'll save for later. But we just want to identify that part B, we're going to be finding the vertex. And then part C, how long is the toy in the air? Well, let's go trace the toy. Here's the toy. It's in the air, it's in the air, it's in the air, it's in the air, still in the air, still in the air, still in the, no longer in the air. So how long is the toy in the air? We want to know how far is it from when the toy is released to the x-intercept. So I'm going to come over here and just label this x-intercept. Now what that is going to do for you is it's going to give you a plan of attack when you're answering the questions so that you know which points you're looking for. And if we come back over here, we do have the skills to find the y-intercept, find the x-intercepts, and find the vertex. That's stuff that we've been working on without any context, which is a little frustrating, but you have the math skills to be able to find that. Again, not today. Today, you're not going to be actually finding the answers to that. Today is all about visualizing. All right, let's look at another one. This one is task card number 4. And this one I wanted to pick because I like the questions in it, and also it's like a slightly different type of motion where like the toy could be going across the backyard. This one is very clearly just straight up and straight down. So a carnival attraction tests your strength by how far in the air you can drive a weight with a hammer. If the weight reaches 15 feet, you win a prize. The equation h equals -16t squared plus 31t plus 2 gives the height h of the weight t seconds after you hit it. How long is the weight moving? What was the weight's maximum height? And question C, did you win a prize and how do you know? So what I want you to do today, again, is just to picture it. So on the next slide, I'm going to start by drawing a picture. So what I'm going to do on this one is actually do this with height h and time t. When you hit the, let's see if I can do this a little bit better. All right, I moved it over a little bit. You have this like game here, and you got this like I don't know what this is, but it goes up to 15 feet. Okay, and on here is some kind of weight, and you hit the lever, and the weight is going to go up, and then it's going to come down. If your weight goes all the way up to the 15 feet, then you win a prize. So what we're going to do is model that here. What you don't know, unless you study physics, is that the starting height is actually 2 feet above the ground. Because if you were to plug in a 0 for t, you would get a 2. You don't really need to know that for doing this. So we're going to draw it like on the ground. The weight is going to go up, and then it's going to come back down. And that's over time. So you're going to hit the weight, it's going to go up, we hope it hits the 15 feet, and then it's going to come back down and land here. In reality, it's going straight up and coming down, but for our purposes, we're going to draw it as a parabola over time. In other words, it starts out going up, and then at some point in time, it starts to drop back down again. So let's label this. We have the y-intercept. We have the vertex, and we have the x-intercept over here. Let's take a look at those questions to see what the questions are asking us for. So the first question was, how long is the weight moving? So let's use our picture to help. You hit the weight, it goes up, it comes down. You hit the weight, it's moving, it's moving, it's moving, it's moving. It actually stops instantaneously at the top, but that's not what the question is driving at. So it's moving, now it's falling back down, moving, 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 stop moving. So when it asks you how long was the weight moving, the number that we want there is x-intercept. So I'm going to come over here and just write in x-intercept. So that question is asking us for the x-intercept. Question B, what was the weight's maximum height? Well, the maximum height was achieved right here. And so for the second one, we would be looking for the vertex. And then the third question, did you win a prize and how do you know? Well, that's going to depend on our answer to part B. We know from the problem that if it reaches 15 feet, then we're going to win a prize. So if the vertex is 15 feet or higher, then we're going to win a prize. If we don't make it to the 15 feet, if it's 14 feet, then no, we don't. And your answer would be based off of the maximum height that the weight reaches. So what you are to do in your groups, if you go into your small group, you will find a file there titled Applications Word Problems. There are 8 problems in there, and your task today is simply to do what I did with these 2. In fact, I've done 2 out of the 8 tasks for you. And so your goal today is just to read each one, draw a picture of what's happening, label the y-intercept, the vertex, and the x-intercepts, then go back to the problem and see if you can figure out each question what you're being asked for. Keep in mind that it might not be any of them. But what I hope you realize is that there's only so many questions that can be asked, and once you get a feel for what those questions sound like, it'll give you a game plan. Next class, we're going to go through, well, how do we actually find these points? So that completes our first lesson on applications of quadratics.